Greeting guys. Welcome to physical chemistry class. So today I want us to focus on the reaction rate. So I want us to quickly consider this graph here, which shows the concentration of a certain reactant, and also obviously it shows what happened as time proceed. So in other words, you will realize that as time proceed, the concentration has been consumed, and doing so, the product has been formed as indicated by this black line here, showing the formation of a product. So now, I want us to define the reaction rate from this point of view. So you will realize that the reaction rate is going to be the change in concentration, obviously per unit time. But then it does not end there. This is the definition of the rate of the reaction, or we can define the rate of reaction as the concentration per unit time. But sometimes one can even define it from other point of view. Like for example, if maybe we have some mass loss, like a weight loss as time proceed, and this results in the formation of a certain product. So this means one can even say what the weight lost per unit time, is still considered a rate, or is still a rate. But in this video, I want us to focus much on the change in concentration per unit time, which is going to be our rate. And let us quickly also, touch the factors that affect the rate of the reaction, whereby we have things like the temperature, catalyst, surface coverage, and obviously the pressure, especially for gases. So these are the factors that affect the rate of the reaction. So now we know that in most cases, when the temperature increase, obviously even the reaction rate normally increase. Same applies to catalyst. You will realize that in situation whereby catalyst had been introduced, the reaction normally proceed faster than a situation whereby, let's say, catalyst was not present. But then we can't talk much of this rate of reaction and forgot about the rate loss, and obviously also the rate constant. So I also want us to touch on this one. So the rate law, obviously let's focus now in situation whereby, let's say, we have A and B that reacted to give us a product. So you will realize that the rate is going to be equals to the rate constant K multiplied by the concentration of the reactant A, and obviously the concentration of reactant B, like that. So now, but then what is this rate law all about? Or rather, what is rate law? You will realize that the rate law is an expression. What expression? Like this expression, right? Which shows the proportionality, or the proportionality between the reactant or the reaction rate. The proportional between the reaction rate and what? And the molar concentration. Molar concentration of what? Of reacting species or the reactant species that are raised to a certain power called the reaction order. So in other words, these reacting species, remember we have A and B as a reacting species, they should be raised to a certain power order, right? In this case, I decided to use P and Q as the order of the reaction. So in other words, these P and Q are the reaction orders, right? Whereby P is the order with respect to reactant A, and Q is the order with respect to reactant B. and we only have A and B here because from our general equation you can see that we have A and B reacting. If now we had even C, like for example, let's say we have A plus B plus C reacting, this simply means that even here we're going to introduce square bracket C raised to a certain power or to a certain order like that. So what about this A and B in square brackets? This A and B in square brackets are the concentration. So this A in brackets is the concentration of A, this one is the concentration of B. And what is the whole of this equation called? This equation, or the whole of this equation, it is called the rate law equation. So this is the rate law equation for reactant A and also B, like that. So what about this K here? So this K is the rate constant for A and B. So in other words, it's the rate constant for reactant A and B. So I want us to look at it in this way. This K is the rate constant of A, and the same K is the rate constant of what? Of B. But in terms of order, this P is the only order with respect to A, and this Q is the only order with respect to B. There is no way that this Q will be the order of A and this P be the order of B. It's not possible. So in other words, the only possibility is when now let's say we have P being 1 and Q being 1. So it is possible that one to have first order with respect to A and first order with respect to B. It is possible to have that case. But then whatever order that is written at this position on top of A, it only represents the order with respect to A. Even if it's 1 here and also 1 here, this 1 is the only order with respect to this A here because it is at this position here. So now I want us to focus much on a situation whereby the concentration has been used up, or as reaction proceed, a certain percentage has been consumed. I want us to focus much on that. So let us consider an example whereby, like what you can see indicated by the red line here, as the reaction proceed, some of the concentration of the reactant has been consumed, or a certain percentage of the reactant has been consumed. Let us consider an example of that nature. So this is the example here. The rate of decomposition of a gaseous compound initially at a concentration of 0.825 mole per cubic decimeter was 1.5 mole per decimeter cube per second. So in other words, this is the rate. You can even see from the units, this one, 1.5. And we are told here that the rate of decomposition is what? Is this one. So this is the only rate when 10% reacted, right? But now, the rate will become this one, or the rate become this one when 40% had reacted at 327 degrees Celsius. Determine the order of the reaction. So in other words, we have one reacting species, which that's why we have only one concentration. So in other words, to find the rate order of the reaction, let's now write the equation first from the rate law, just from the previous page. We defined the rate law, and the expression was of this nature. We have K rate is equal to Ka to the power, let's say, letter P. So this is the rate law, and I only wrote A. We don't have B in this case because we have only one reacting species from this concentration here. So now, from this one here, let's now check what happened as the time proceed, or what happened when 10% reacted. So let's find the concentration when only 10% reacted. So the concentration, let's call it first concentration, or A1. Let's call it A1 because we are focusing on a situation whereby only 10% reacted. So let's call it concentration 1, or A1. This is going to be equals to the initial concentration minus what has reacted. in this case is going to be the initial concentration multiplied by 10%, because 10% had reacted, so it's going to be 10 over 100%. So when we press a calculator, this is going to give us 0.7425 mole per cubic decimeter. So in other words, this is more like a change in concentration. Remember, as time proceeds, a certain concentration has been used up. So in this case, 10% has been used up, or they had reacted. So the change in concentration is what we were looking for, because from even the definition on the previous page, you will realize that the rate is defined as the change in what, in concentration per unit time. And even time is considered in this case, because the rate is in the form of time. You can even see here that the rate do consider or do take time into consideration. We have time in a second, like that. So in other words, this is the concentration, or the first concentration when 10% reacted. Let's find the concentration when 40% reacted, right? Or before then, we can even find the rate, or rather write the rate down, the one that we are given. So the rate is 1.5 mole per cubic decimeter per seconds. So this is it we are given. So this is more like it. So this is the rate 1, the first rate. The second rate is this one here. But now, before we go to the second rate, let's find the second concentration. This is the concentration when 40% had reacted. So again, it's going to be the initial concentration, which is 0.825 minus 0.825 multiplied by 40%, because this is the concentration when 40% had reactant. So the answer, if you press a calculator, is going to be 0.495 mole per cubic decimeter. And if you check the units, you will realize that this is the units for what? For concentration, because it's mole per cubic decimeter. If you check this one out, the units for rates is mole per decimeter cube per second, like this one. So what about now the second rate? The second rate is given is this one here. This is rate 2. So we are going to write rate 2 like this, and we will copy it down to say rate 2 is equal to 1.00 mole per decimeter cube per second, right? And then from there, let us now consider the ratio. So if we were to take the ratio between these 2 and 1, we can come and say, let's say rate 1 over rate 2 is equal to K initial concentration 1, or not, change in concentration of 1 to the power P divided by K multiplied by the second concentration to the power P, or the change in the second concentration to the power P, like that. So we know that rate 1 is this one here, right? So rate 1 is going to be 1.5, but don't forget the units, it's mole per decimeter cube per seconds. This is going to be divided by rate 2. Rate 2 is this one here. Rate 2 is this one, and they're given actually, even in the equation, they're given. So rate 2 is this one. I'm saying it's rate 2 because even in terms of appearance, can you see that we have this rate, it appear first, I call it 1. Obviously, it correlates with 10% reacting. That's why everything, this one and this one, they correlate with this one here, this one. And then this is the second rate to appear, right? Because the first one is this one to appear. So this second rate is the one that correlates with 40%. That's why I introduced 2 here, this 2 here, and this 2 here. So rate 2 is going to be 1.00 mole per decimeter cube per seconds, because it's the rate. And then this is going to be equals to remember concentration rate constant cancel this rate constant here. So underneath A2, or the concentration, the second concentration is going to be 0.4495 mole per decimeter cube to the power P. This is the second concentration, right? And then on top we are going to have what? The first concentration, this one here, right? And then this one here, which is A1, is what is this one, 0.7425. This is going to be our first, right, concentration, mole per decimeter cube to the power p, like that. So from there we can divide this one by this one. We're going to have 1.5, and then when we divide this one by this one, we are also going to get 1.5 to the power p. But then if you check this 1.5, it's more like it's 1.5 to the power 1. It's just that we don't write it, right? So now if we have 1.5 to the power 1, and we also have 1.5, this one here, to the power p, since 1.5 is the same as 1.5, automatically p should be the same as whatever that is on top here, that is not written in this case, which is 1. So this, or it is due to that reason that the value of p is going to be 1, and it will simply means, or this simply means, that the order of this reaction is 1, or this reaction is the first order. So thank you so much for watching this video, and please, if you haven't subscribed to this channel, kindly join this growing family by subscribing to this channel, and I thank you.